Uh, Hello Nadir. We are going to do resistance and resistivity today. Last time we did Kirchhoff's laws and before that, so we are going deeper into this exploration of circuits and the components of the circuits that we have talked about, right? For now, we have seen things like a battery. We have seen things like a voltmeter, an ammeter, which are measurement instruments. We have also seen resistors. We have seen there are a few other components for which we have discussed the symbols of in the first one. And of course, those symbols are important and you should remember them. But in this chapter, we are exclusively going to talk about two things, which is resistance, and then there is a generalization of resistance, which is called like Ohm's law. So we're just going to talk about that, and then one more component that we're going to talk about is a thermistor, right? Thermistor is nothing but a temperature dependent resistor. So whose resistance changes with temperature, right? So we are going to see now change. You might ask whether it increases or decreases. So it can be either. So if it increases with temperature, it's called a PTC thermistor, which is a positive thermal coefficient. So temperature rises, resistance rises. So positive. Or it can be an NTC resistor, negative thermal coefficient. So temperature rises and resistance decreases with temperature, right? So we're going to talk about this thermistor component a little bit. We're going to talk about Ohm's law and we're going to talk about resistivity. Should not be very complicated. It's a theoretical kind of a thing. Unlike chapter 9 where we were dealing with a lot of circuits, this will be more of a discussion where you'll have to listen. There might be a few sums I might give you towards the end, so we'll see how that one goes. But let's get started. Okay. So the first thing that we talk about is something called an IV characteristic. Uh, so IV characteristic is nothing but something like this, right? So you have a circuit like this. So you have whatever component you want to measure. Sorry about that. So you have whatever component you want to measure. It can be a resistor, it can be anything, right? Let's just call it a component, right? Across that component, first of all, you will give a some voltage, right? And because you give some voltage and EMF across it, it will have some current that will flow into it which you want to measure. So you'll put an ammeter in series, right? It will intercept the current and measure it. And across it you'll put a voltmeter to measure the voltage across it. Right? So what you try to do is you keep changing this value up or down, right? And that will change this current that's flowing into this component. So imagine if it was a resistor and you had 1 volt, then 1 ampere of current will flow. If you had 2 volts, then perhaps 2 amperes of current will flow. And these two components will tell you exactly those components, right? Then what you try to do is you try to plot this on a graph. So you say that the current that the ammeter measures is on the x-axis, on the y-axis, and the voltmeter, the voltage that voltmeter measures on the x-axis, right? So and you say that okay, I gave one this thing and I got this. I gave two, I got this. I gave three, I got this. I got four, I got this, right? And it clearly looks like the trend. If you connect the line, it looks like a straight line, right? Well, another thing that you can do is you can go in maybe the opposite direction. You can flip the polarity of your battery. You decide to connect the battery the other way around, right? Maybe you try to flip it and then you see that the trend also is like this, right? So we are in the negative half of the plane, so voltage is negative, means that it is flipped. So current is also negative. So right, so voltage is negative and current is also negative, which should be the case. So we see something like this. So this is what we would say is an IV characteristic. By IV, I on the y-axis, x on the z on the x-axis, IV characteristic of a resistor. Maybe this is what you see. So you say that if I have 1 volt of you applied 1 volt, you get 1 ampere out. If you applied 2 volts, then you got 2 amperes out. So you say that maybe you can find the slope of V by I, and you say that that is equal to 1 in our case, right? And this, if this slope is a constant, then we say that this is equal to the resistance of the of this component. So the thing is, it can also not be uh, it can also not be a straight line. So let's talk about that also a little bit. So it can be something like, so there are some components, right? So maybe there is a component called like a diode. Okay, so the role of a diode is, I don't know if you know, but role of a diode is to only allow signals to, like current to through pass through this way. So what that means is, if you apply a positive voltage to the battery, then you will see some current flow. But if you flip the polarity of the battery, then no current will flow. So in that kind of a case, you will have some, so on the positive side, maybe at this point you have some current, in this another point you have more current, but then at lower values it switches off, something like this. So like at, maybe it's like this at some higher value. So this is V, this is I. So you see that till this point it was off, it was not allowing any current. And this, at, if it is a modern silicon diode made out of silicon, then it will be at zero point 0.6, it will start conducting if you apply zero point 0.6 volts of it, and it will just conduct. But if you connect it the negative way, then nothing will go through, it will just be staying at 0 all throughout, right? Because if you flip the polarity, nothing will happen. So in this kind of a case, you see that, okay, I apply a voltage of 0.1, then if my voltage was 0.1, my current was 0. If my voltage was 0.2, then my current is still 0. Did my current double? No. So this is not a resistor. Or what we can say that, so if it follows a straight line, we can also say that it is an ohmic component. Ohmic component. If it has a straight line graph. Does this have a straight line graph? No, it does not. So not an ohmic component. That is to say, it doesn't obey Ohm's law. What is the Ohm's law? Ohm's law is when you have resistance like behavior. You put a voltage, you get a current. You double the voltage, you get double the current. But if you don't get double, maybe you get half, then it's not an ohmic component. So let's look at one more component that your book discusses, which is called a thermistor. In particular, we are going to talk about an NTC thermistor. So what that does is something like this. So let's talk about it. Okay. So just to repeat the statement of Ohm's law, it says that a current of a conductor obeys an Ohm's law if the current is directly proportional to the potential difference across it. So whatever the potential difference is, if the current is directly proportional, meaning that potential difference double, current double, then it is an ohmic component. Okay. So if you have, so the first thing that they discussed here, it is about a bulb, and what they saw was, as the voltage increases, as the current increases, they say that, okay, initially you double the voltage. If you have a voltage at around here, you double the voltage, current also doubles. But if you are somewhere around here, and if you double the voltage, like maybe this is your other point, this is zero point 0.5, maybe this is 1, then you see current has only increased by a small amount, it has not doubled. Like, so if we were to, so let's see, so instead of thermistor, let's first discuss a bulb. So it can be any electrical component, you see. So they are telling us that the IV characteristic of a bulb looks like this, right? and then it looks like it is peaking, it is plateauing at the edges. And the point is that, 1 second, my Jamboard just lagged out. Maybe there's an issue. Yeah, so so this is maybe the IV character. So if it was an ohmic component, this trend would have continued. So if you applied, you see, if you applied this voltage and you doubled it, then the current doubled, right? But if you applied, say, maybe this voltage and then you doubled it, then you would have expected this amount of current, right? Right at the top, this much amount of current. But it seems to not be the case. The current produced is only this much. So we say that at small values of V, it is ohmic. It is like a resistance, but at higher voltage, you see that less current is observed for the same voltage. So if less current is observed for the same pushing power, that means it is resisting more. So the resistance is higher than at low. So at this point, if you observe the resistance, then it will be V by I will be, this will be higher than this guy, because at this point it's allowing the it more current to pass, right? So this is what your book talks about. So is this component ohmic? No, it is not ohmic. Okay. Then we talk about these thermistors that are talked about in your book. So the idea of negative uh, negative negative thermal coefficient thermistors. The idea is as temperature increases, resistance decreases. So if you plot it like this, and if you have a temperature on the x-axis and resistance on the y-axis, note that this is not an IV characteristic. So it looks like the the resistance at some point is high, then it starts to decrease, something like this. So this will be a negative thermal coefficient, NTC thermistor. If you had, on the other hand, a PTC, then it would look like this, a positive thermal coefficient, right? So this is what your book also talks about. So let's go through that a little bit. I would encourage you to do this one on your own, question 3, and just read through this theory a little bit more to understand. Uh, so can you just like pause the video and think about which of A or B obeys the ohmic law? And if it obeys the ohmic law, what is the resistance that's seen by that component? Can you take a guess? Okay, and what is the resistance? Right. So we see that B should be the ohmic component because it follows a straight line curve, and A is not a non-ohmic component. And the resistance of B will be given by, you take any 2 points, right? You say maybe 6 voltage, and then it is 2.6 maybe. So 6 by 2.6. Note that it is not 2.6 by 6 because it is voltage by current. So another point to note here is the inverse of gradient is the resistance. So gradient gives you I by V at this point, which is the slope of the line, but you want to find 1 by a gradient to find the resistance. Okay, then here they talk about that the diodes. One thing that we say that diodes are used as rectifiers. So we'll see how that is in the next chapter, hopefully. Uh, and there's also something called a light dependent resistor. So the idea is as the light that falls on the resistor increases, then the resistance decreases. So maybe you have those lamps, right, that glow when you turn off all the lights. So they just are plugged in. As soon as there's a lot of light in the room, then there's no, they don't glow. But as soon as you switch everything off, they just start glowing like a night lamp or something, right? So they are made by something like a light dependent resistor. For a diode, so sorry, for a thermistor, you also have uses like, so you have temperature sensor uh, on some cars. So those temperature sensors usually work by this thermistor kind of a thing. So wherever you want to sense temperatures, it's usually a resistor that is temperature dependent. Okay, fine. And then they talk about this for normal resistance. So we talked about this temperature dependence for thermistor, and we saw that it increases, right? So what do you think will be the graph for something which is more flatter, like something like this, which will be a normal resistor, right? We would think that maybe the resistance remains constant with temperature, but that's truly not the case. It seems that the resistance actually increases just a little bit. So in some sense, it is a positive, a PTC resistor because it is increasing with temperature, but it's so slight that we don't like to call it that. So something like just very slight increase. So and we also see that if it is pure, then the resistance is lower. If there are some like defects or impurity in the lattice of the conductor, then it increases the resistance a little bit. So in the same idea, if you would know, so the spectrum would lies from, so yeah. So the spectrum lies from, so the on one end you have conductors, then you have semiconductors, and then you have insulators, right? So these are like pure metal, right, on one end, and then you have maybe plastics and like things which are not that conductive on the other end, like maybe also wood, right, which are not that great on the other end. On the semiconductor side, you have, which is the more gray area, you have silicon based or germanium based lattices on in the middle, right? So let's talk about this a little bit more, all three. So the idea about conductors, if you remember, we had talked about it in two chapters back when we were introducing. We said that there is a sea of electrons, and then there are these positive cores that are lying, right? And if you have to say push current through, then that means that the sea of electron must move, and when it moves, then it collides with all of the positive stationary positive charges that are there. So the idea is, say, if you increase the temperature of this wire, what do you think happens to the current that passes through it? Take a guess. When you can pause the video also to think about it. So when you increase the temperature, then they start wiggling more. The lattice, the positive cores start wiggling. They don't move, but they just move a little bit more in their space. They start vibrating a little bit more. So the sea of electron that needs to pass through them then encounters more collisions and resistance, right? So it just stops and like as is struggling to make it through. So which is why this behavior we see that with temperature increases, the resistance increases slightly, right? That explains that. And the another thing about that also explains this impurity curve. Why is it higher than this? Because if there are impure things, then maybe there is a lattice that you have that's regular of all the atoms, of all the positive cores, but then there is one big atom in the middle because of an impurity, right? So when it vibrates, you can imagine that. So your book actually talks about this really nicely. So if there are see bigger atoms right here, then they also struggle to go through them. So if there is any strugglance, if there is any resistance, a resistor, so its resistance will be higher. If so, this acts more like a resistor. So higher temperature and more impurities are a problem. Okay. So this is about this end of the spectrum. So we said that on this end we have a temperature issue. Maybe let's write it with a different color. So maybe at this point we have a temperature. So temperature and impurities govern resistance, right? So they control how much resistance a component will have on this side. So let's go towards the other side. Let's talk about semiconductors a little bit. Semiconductors usually don't have this sea of electrons. The sea of electrons theory is only true for electrons, or if only true for conductors. So semiconductors basically they keep their electrons to themselves. Remember, the sea of electrons was formed because all of these cores gave away one electron and hence became positively charged themselves and gave away that electron which was free to move. But semiconductors like to keep the electrons to themselves. They are near in the middle of the periodic table. If you see, silicon is somewhere in the fourth group, and so that's more this thing. But copper and all, if you see, they're more towards the metallic side. So these semiconductors like to keep to their electrons. But so what happens when you give a lot of overall uh, their current, their resistance is much higher than that of a conductor, and their currents are much lower because you don't have this sea of electron that's passing through. But when you give them temperature, then they start vibrating and they start letting go of their electrons. So that adds to the sea of electron, that makes a sea of electrons. So that increases current. So another factor that you have here is similar to this thing, which is a temperature, right? So you need to think about the component that you're dealing with. So you can imagine that maybe semiconductors are less like an ohmic component than a conductor is. So and in insulators they mostly don't do anything with temperature. They just have a high uh, resistance throughout, like much higher than semiconductors or conductors, right? So it also makes sense why we call semiconductors. They're somewhere in the middle. Their resistance is somewhere in the middle. Their conduction is somewhere in the middle, something like that. So here, again, just to repeat, so here temperature increases for conductors, then the resistance also increases because of that extra collision that happened. But in a semiconductor, when temperature increases, then the resistance decreases. This resistance decreases because more charge carriers, more electrons are given out of those cores, and then that adds to that overall flow. So yes, the collisions also increase like in the case of conductors, but more and more electrons are given up. So that adds to the flow. So that's the dominant factor here. Okay, and the last thing that we talk about here in this chapter is this idea of this resistivity. So the idea is we know that in this picture, if the length of the wire is longer, then the resistance will of course be longer, right? There will be more collisions and all. So that makes sense. And then we also say that if the wire is wider, then it has that sea of electrons maybe has a wider area to pass. So it's an inverse relation to area. So if area increases, then the resistance decreases of a wire. So then we combine these two into this common formula called R is proportional to L over A. So L increases, R increases, A increases, then R decreases. So we have this, and then we add a constant of proportionality, which is called resistivity. So this constant of proportionality is different for different materials. So the idea of constant of proportionality are that if you make these two 1 and 1, right, what is the resistance that you measure? So for 1 meter length and 1 meter square uh, component, what is the resistance that you observe? So as you can imagine, if it's a copper wire, you might observe a different resistance. If it's a gold wire, then you might observe a different resistance. Silver wire, different. So this component is like describing the amount of resistance for a uh, unit length and unit cross-sectional area, right? So and that we call resistivity. So we can see that different values of resistivity are given here. It looks like silver has the lowest resistivity, meaning that for one L1 and 1 area, you have very low resistance. So that indicates conductor-like behavior. And then you go down, so silver is good, copper is good, which is why you make wires out of them. But we don't make wires out of silver because it is very expensive. Copper is relatively cheaper, so we use copper. Then we go down, aluminum is good, lead is good. Then we start to get into this middle area. Graphite is amazing. Then we go down, then we get into germanium silicon. These are now this is semiconductor range. So you can see that this is very, very small, 10 power minus 8, and this is like single order or higher. This is very high. So this is like about 11 orders of magnitude difference between these two. Then another roughly 9 orders of magnitude if you go up. So these are strictly, the last three are strictly insulators, right? So from one length, one, they have a very, very high resistance. So this is how you see. And of course, we talked about how resistance and temperature, and we saw the inverse, the opposite trend in conductor and resistor. That is more or less all. Let's see. So in terms of questions, you should definitely attempt problem 3, question 3 here. Question 3, not this one. Yeah, so you should attempt question 2 here. Also look at question 3 here. Yeah, so 2 and 3 right here. And yeah, let's do this one as well. 2, 3, 5. Sorry. Uh, yeah, so this we have already discussed. So 2, 3, 5. And yeah, let's do this one as well. 2, 3, 5, and the and 8. Mm, yeah, 8. Just do one question of this one and any one of these. It's okay. So I'll just write it here. What is the homework? So that will be 2, 3, 5, 6, and then finally you have 8A, and then maybe one of 9, 10. So this is the exercise to do. Okay. See you next time. I hope this is good. So we have kind of completed this. So we'll do one more thing about circuits, and then we'll be done with circuits. So the whole idea, just to summarize a little bit, we discussed about current and voltages and meaning of all of them in the initial one. So resistance, power, current, voltage, these are the general terms that we dealt with. Then we dealt with some circuits. We got one level down where we dealt with Kirchhoff's first law, which was about current adding and subtracting. Then the second law where we were dealing with voltage additions and voltage subtractions, EMF components. And the last thing that we did was thinking more about the IV characteristic, the temperature dependent behavior, the voltage dependent, the ohmic laws. And then we also looked at more components like diode, thermistors, and whatnot. And then we finally broadened our discussion to semiconductors also by including this parameter called resistivity. So this is the idea. Now we'll be also looking at some practical circuits in the next one, and then we'll be done. Okay, see you next time.